All right, this is the review video for the central tendency quiz, which is scheduled for Monday, February 6th. If you're going to do central tendency, usually mean, median, and mode are things that most people at this point know how to do. And the new thing was the standard deviation. So the first thing you usually want to do when you're dealing with mean, median, and mode, especially median, is to put the data in order. So I went ahead and did that real quick, like this. So as far as calculating a mean is the same thing as an average. So you want to add up all these numbers and divide by how many there are. So calculating the mean is just as simple as adding a bunch of numbers together. You can use a calculator if you want to make it go a little quicker. And when we do that, I get 145. I'm going to be dividing that by the 13 numbers. That gives me a mean of 11.15 with a bunch of decimals. Let's get around to 11.2 for the mean. The median is the reason why you put the numbers in order. You want the middle number. So there are 13 of these. So right now, I would say I want 6 on each side of the middle. So I got 1, 2, 3, 4, 5. There's the 6th number. It means this one is the median. So the median is 9 for the middle number. And then we also want a mode, which is the most frequently occurring number. And as you can see, the 9 shows up 3 times in the data set. None of the other numbers more than twice. So the mode is also 9. Okay, now we're going to deal with the standard deviation. And this takes a little bit of time to do, especially when you have a mean that is a decimal. So it's going to take a few seconds here, but basically your first thing you want to do is take your mean and look at your data set and say how far off are each one of these numbers from the mean. So if we compare 11.2 to 3, I'd say that is 8.2 places or numbers off from the mean. And I'm going to do that for each one of these numbers here. Okay, so I've made a list of how far off each data number is. Each one of these is from the mean. The next step is to take that number and square it, which means 8.2 squared, or 8.2 times 8.2. That gives me 67. I'm going to round these also to one decimal, so 67.2. And once again, I'm going to go through and do that for all of these numbers. Okay, so now looking at those, after I squared them all, you can really see how much different this last one is compared to the others. That's really going to make your standard deviation be way off from what it should be. And that's what an outlier does to the data. So this number 41 up here is really messing with our data because it's way different than all the others. But for now, it didn't say to leave it out, so let's just calculate it. Now what I'm going to do is take all of these numbers, I'm going to add them all up and divide by how many they are. Essentially, I'm taking an average of all of these numbers. That number that we get, that average, is called the variance. Okay, so when I do that, I added them all up and I divided by the 13 to get the average of 83.6. You should know that this number you get is called the variance. And then to finally get the standard deviation, which is what it asks you to begin with, all you do is square root the variance value you got. When you do that, you get 9.14, which is your final answer for standard deviation. That's pretty high, which tells you that the data points are pretty separate and pretty far apart from the mean. But again, realistically, they're not that far apart from the mean for the most part. The only one that's really, really far off is the 41. And if it wasn't for that number, this standard deviation would not be as high. And actually the median, or excuse me, the mean would also not be that high. So what's the outlier? The outlier is definitely the number 41 in this data. So if we go over to the next page, it says remove the outlier and calculate the mean, median, mode, and standard deviation. So it's asking you to do the same exact calculation, except they want you to take the outlier out of things. That may seem like a crazy thing to do and another really long problem. And I guess it sort of is kind of long. If you remember, though, the math isn't really that bad. But it's just sort of lengthy. The thing to understand is, though, that if you're really doing a standard deviation and you really want to know what's happening for whatever these numbers are supposed to represent, if you really want to know what's going on, you can't have outliers in there because they really mess up just about everything. So what they're saying is cancel out this outlier and do the exact same thing you just did. So let's go through and do it one more time. And this time we'll forget about that outlier. So I need to add up all those things again. When I just did it a second ago, I got 145. So I'm just not including the 41. So I'm going to say that total comes out to 104. And then I'm going to divide it by 12. Which gives me an 8.7 for a mean. Okay, let's look at the median. Again, we only have 12 numbers now, so that might change too. I need 6 on each side. 1, 2, 3, 4, 5, 6, and then there'd be 6 this way. So what happens is the median ends up being between these two numbers now. And that's okay, because really what I would do is add these two numbers together and divide by 2. Since they're the exact same number, I think you know that the median is going to be a 9. And the mode, well, taking that outlier out didn't really change how many times the 9 shows up, so the mode is still 9. Outliers usually don't affect the mode that much. Sometimes the median, always they affect the mean. Okay, so now it's back to going standard deviation again. So I have a new mean now, so I kind of have to redo all those numbers. So if you did your problems by just deleting the last number here, it's logical reasoning to a point, which is okay, but the problem with that is you have to remember that when you take out the outlier, you recalculate the mean, which means that you need to subtract all of those numbers or find the difference of all of those numbers in the new mean, not the old one, which is what you did a minute ago. So it is going to be a little bit different because of that. So let's take a minute and figure out the difference between each one of these points and the new mean. Okay, those are all the differences now. If you look at those compared to what we had before, we have a lot of numbers that are a lot closer than they were before. We don't have any that's nearly as far off as that 29.8 was. So we go back to this. Now we got to square all of these numbers. So again, let's take a minute and square each one. Again, that would mean 5.7 squared, or 5.7 times 5.7. For that one, I get 32.5. So let's take a minute and figure out all of those. Okay, so at this point, we've got all the squares down again. And now we need to average all of those numbers, all of these. So we got to add them all up and divide this time by 12, because there's only 12 numbers. Let's do some quick addition. For all these decimal points, you really have to be careful that you type in the numbers correctly. So if you just take an extra second to make sure you're doing that, make sure each thing you type in registers what you wanted on the calculator. It'll be very worthwhile to you. I've got 122.8. So now I'm going to take that and I'm going to divide it by 12. I get 10.23. Again, that's the variance, right? So the last step is to square root the variance. You get 3.2. So by taking out that outlier, we've got a more sensical average. It's 8.7. So the mean went down, which makes sense because we don't have this really high number affecting things. And the standard deviation went from 9.14 down to 3.2, which tells you that the data points are now much more consistent. They're closer to the mean. That means that you have sort of good data. You have a mean that's 8.7, and it makes some sense when you have a low standard deviation. It says all the scores are relatively close to that mean value. If you can understand that, you've got standard deviation down. No problem. All right, so the last part of dealing with this data set asks you to make a box and whisker plot. So what I'm going to do to make this a little bit easier is I'm going to put a grid up here and do this on graph paper. That way I make sure my numbers that I'm writing on here are as accurate as possible. But when you do a box and whisker plot, you really shouldn't account for any outliers in the data. So we're actually going to basically leave this out. I'll show you in a minute what we do with it. But for now, we're going to pretend that it's not even there and just do a box and whisker plot off of the data that was realistic. So we already have it in order. You're basically going to look for a few things. The first thing you want to do is find the median of the whole data. We did that a little earlier. We said 6 numbers on each side. So that median is right here. It's a 9. Now you actually want the median of the lower half, which is between the 5 and the 7. 5 plus 7 is 12. Divide by 2, you get 6. And you want the median of the upper half. Again, stop at the 14. So 6 numbers on this side is between the 10 and the 12. 10 plus 12 is 22. Divide by 2, you get 11. So we got those numbers to help us with our box and whisker plot. Okay, so let me add this graph in here just to make this a little easier for us. Okay, first thing I want to do is I want to make a number line. So let me find that. That's probably long enough, I guess. Okay, now I need this number line to go from 3 up to 14. I want to make sure they fit. So I'm just going to start here with the 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. And so I made this number line really long. I don't have to make it that long. Sometimes, you know, it's good to have a little extra space, but really we don't need a whole lot. So I'll go up to 15 to 16 here, and then I can stop. All right, so I want to put the box in first, and the box comes from these 3 numbers. The median, like this number is one side of the box, so let's put it here. That's the first quartile, as we call it. The 9 was the median line, let's put it in. And 11 is the upper quartile, or the other side of the box, so we'll draw it in. So there's the box, like that. And then you need the lowest point, which is 3. We're going to put a dot there, and then connect it, and we make one of these whiskers. And we do the same thing on the other side. 14 is the highest. We'll put a dot there, and we'll make the whisker go that way. So there's your box and whisker plot. The only thing is, what do we do with that 41 up there? Well, for the most part, it isn't really part of the box and whisker plot data at all. The only thing that does matter is you should actually sort of include it. So what a lot of people like to do when it's way far off is they do one of these breaks in the number line, like that, to tell people that you've broken the line. And then over here at 41, you can just go like that and say, look, we're cutting out all the stuff between 16 and 41, we don't need it. People will put a data point there. You don't connect it to anything, it just shows that there was an outlier in the data, like that. So it really says, the box and whisker says all the stuff that's down here that really matters, but just so you know, we did have an outlier out here too, in case it might matter for some reason. So outliers really aren't part of it, but usually they are represented on the graph. All right, so here's the box and whisker plot that is drawn on your paper, and it asks you to answer a bunch of questions about whether or not you can determine some of these things based just on the graph, not making the plot, but actually seeing if you can read the one that's made for you. So in this case, we're saying, what's the median? Well, the median is this line right here inside the box. The median is 15. That's easy stuff. The interquartile range is almost as easy. It's between the quartiles, or the length of the box. So from 13.5 up to 18. 13.5 up to 18, that's a distance of 4.5. What's the range of numbers that represents the bottom 25%? Well, you should know that the box and whisker plot is divided into percentages. This represents 0, 25, 50%, 75, and then the 100% mark. So the bottom 25% is the left whisker, and it goes from 7 up to 13.5. How many students scored in the top 25%? This is sort of a trick question. It tells you that there are 20 students, 20 test scores to worry about. So if there's 20 students, all you really do, it actually doesn't have much to do with the box and whisker plot. Take 20, take 0.25 and multiply it by the 20 people that took the test, and you get 5. This is important because it's important to realize that each one of these sections really represents 5 students. 5 in this 25%, 5 here, 5 here, and 5 here. So even though the lines are longer, it doesn't mean it represents more people. What it means is the 5 people that scored in the bottom 25%, their scores range from 7 to 13.5. That still was only good enough for bottom 25%. Whereas over here, the 5 people that scored on the top, theirs went from 18 to 20. So it's a smaller range, but it's not a smaller amount of people. Number 10 says, what score did you have to get to finish in the top 25%? Well, let's say you got to get at least a minimum of 18. This top whisker represents that. So you got to get something between 18 and 20. You wanted to be the 50 to 75% range. Between what 2 scores would you have to fall in between? Okay, right here you can see, here's the 50% mark, the median. 75 is that upper quartile. If you want to be in that range, you got to be from 15 to 18. All right, the first one that's really tough here says, did the students do on this test in terms of passing? I guess it's supposed to say, how do the students do on this test in terms of passing grade? Must be a typo. So it says, remember, passing grade is 66% or better out of the 20. So really it's asking you, do you think the class did well overall? Well, 66% is passing. So the first thing we need to know is, what is a passing score? If you take 0.66 and multiply it by 20, what you get is 13.2. In other words, you need 13.2 to pass. So where is that on the graph? Well, that's like right here. That's the passing score. So if you understand how to read a box and Whisker plot, what it's telling you is here's the top 50%. They all pass. Even right here, that's the top 75%, right? The Whisker represents the bottom 25. So right here, this edge of the box is ahead of the passing grade. That means the top 75% pass. And even maybe some of the bottom 25% actually pass. So just because you were in the bottom 25% didn't mean you automatically failed. So I would say, yes, for sure. And what you can say is at least 75% of the students pass. Of course, ideally, we'd like to see 100% passing. But 75% is pretty good. Okay, would you expect the standard deviation to be low or high? Really tough question because it's requiring you to kind of look at this data and make a few estimates and assume a couple of things. But I think you can do it if you understand standard deviation. Remember, standard deviation, like we did on these other problems back here, was all based off of what the mean was. Right? And then low standard deviations meant the data was relatively close to the mean overall. So here's the thing, if you're looking at this graph, most people assume the average is right at 15, where the median is. Well, not really totally true, but it's not a bad place to start either. If you say, okay, well at 15 I've got up to 5 ahead of that, and I've got all the way down to 13 below it, or excuse me, 8 below it. I'm thinking the average might be just a little bit less than that, so I'm just going to estimate it and say the average is 14. Again, it's just a total estimate. Well, if the average is 14, I've got a lot of numbers ahead of it, but they're only ahead of it by a maximum of 6. And I do have a decent amount of numbers below it too, and they're only below by 7 though. So realistically, I've got a range of numbers that falls between 7 and 20, and my average is roughly 14. I have a few numbers above, I have a few numbers below, but they're not too far off. So the explanation for this, I would say the standard deviation is low, or at least kind of low, and that the explanation is real simple. It's to say because the data is relatively close to the mean. And again, it's only an estimated mean, but you get some idea of what it looks like. So number 13 is unlike the other one. Number 13 doesn't really have a hard and fast answer to it. What it has is an explanation that really depends on how you look at it. Some people might say that those numbers are really far off. It all depends on how you want to make that argument. But the key is that understanding what standard deviation means, which is that low ones are close and high standard deviations mean the numbers are far off. All right. Last but not least, we have means versus expected value. The idea behind these problems were to show you how different an average and a weighted average or an expected value can be. Excuse me. So again, we have a little bit of calculator work to do, but it really shouldn't be nearly as long as the other stuff. So it says do two things: find the mean and then find the actual expected value. So let's start with the mean. The mean is just adding up all of these numbers on the top and dividing by how many there are. So very quickly, it looks like I have $1,126. I'm going to divide that by 6. Comes out to $187.67. So if everything were to occur equally, in other words, you had an equally likely chance of getting 1,000 as you did a 0, you should expect your average win to be $187.67. But we know that any kind of prize, they're not going to make the idea of winning 1,000, the grand prize, the same kind of probability as winning nothing. So expected value is going to take into account this probability of it happening. So you actually want to take the value times the probability. So it takes a second to do that, but this one's going to be 0, because we know 0 times anything is 0. The next one is 0.05. The next one is also 0.05. The next one is 0.06. The next one is 0.1. And the last one, I think it's also 0.1. Yes, it is. So when you do expected value, you actually just want to add up all of these. When you're working with probability, it makes it easier because probability incorporates everything you need to just by multiplying them. So when you multiply each one and add them all up, you get 0.36. So the funny thing is the average, if everything worked out evenly, would be $187.67. The truth is that if you were to play this prize giveaway, the real expected value, what you should actually expect to win, is 36 cents. So it's sort of misleading in a sense to say, look, you know, you only have 6 possibilities. Yeah, that's true, but there's a much higher probability the way they work out the game that you don't win anything. So high, in fact, that your actual average, your weighted average, or what we call expected value, really is only 36 cents. Okay, so number 15 is the other style of problem. Number 15 deals with a frequency table rather than a probability. So it's basically the same idea. Take whatever it is on the top, and the first thing we're going to do is average them all up. So I have 4 plus 3.5 plus 3 plus 2.5 plus 2 plus 1 plus 0. And I got to divide it by 16. I'm going to divide it by 1, 2, 3, 4, 5, 6, 7, divide by 7. I get about 2.3. So if everything was equally likely to happen, your average should be 2.3. In other words, just by the possible star ratings, you would expect to get an average of 2.3 stars for your movie. But again, that assumes that each of the star ratings comes out relatively equally. And you can see by the frequency table that that's not true. Look how much more often 2 stars happen than nothing, or how much more they happen than 4 stars. So you should expect that maybe that 2.3 isn't totally right. So when you're dealing with a frequency table, one of the first things I suggest people do is total up how many of these numbers there are, because you're going to need that in a minute. So just looking at it really quickly, I've got 25, 30, 44, 52, 61 total. Now I need to multiply these together, just like I did above it. So I've got 20. 3.5 times 8 is 28. 3 times 9 is 27. 2.5 times 14 is 35. 2 times 18 is 36. 5 and 0. Now I'm going to add them up just like I did all of these. So I've got 48 plus 27 plus 35 plus 56 plus 5. I end up with 151. And then, to finish it, the reason I did this, divide, 151 divided by 61, you end up with 2.4748, 2.48. So this time the expected value isn't that much different than the average, but it is a little bit higher. So it tells you that it's much more likely to be 2.5 stars based on the actual probability of things, because of how many times all of these bigger ones occur compared to the low ones. So it tells you it's tilted a little higher than what the actual average is. It's really not that different, but sometimes you see that kind of a thing, right, where it's a little bit biased because it's very hard to get a no star moving. Right? So this is the expected value for the frequency table. And the key understanding was how to do it differently. When it's probability, you just multiply each column and then add it all up, and that's the expected value. If it's a frequency table, you have to multiply each one and add it all up, just like you did in the other one. But you also have to divide by the total number of the frequency items to finish. Okay, that's it for the probability, or excuse me, expected value and all of the central tendencies. I would say that if you get this down, you probably have a pretty decent understanding of basic statistics for Algebra 2.